Are we alone in the universe? Or is there intelligent life out there that we've yet to discover? Could advanced civilizations be hiding from us? Or are they preparing to launch an attack? And what if the key to unlocking the secrets of the universe lies in the existence of silicon-based life? Join us on a journey through space and time as we explore these questions. From the possibilities and challenges of interstellar travel to the paradoxes that confound our understanding of the cosmos. This video will take you on an unforgettable adventure into the unknown. Are you ready to discover what lies beyond the stars? The dream of exploring the depths of space beyond our solar system has long captured the imagination of mankind. But is interstellar travel just a distant fantasy, or can we really achieve this goal in the near future? Thanks to the scientific and technological advances made in recent years, we're closer than ever to interstellar travel becoming a reality. The development of new propulsion systems, advances in material science, and our understanding of cosmological theories brings us closer to developing the necessary infrastructure and technology for interstellar missions. However, this ambitious goal has its challenges. The vast distances between stars and the large number of threats lurking in outer space make interstellar travel difficult and potentially dangerous. If we're being optimistic, and certainly not unrealistic, humans will be able to achieve interstellar travel within our lifetime. The possibilities are endless, and the rewards could be extraordinary. The difficult task of interstellar travel is primarily defined by the vast expanses between stars. Our closest neighbor, Proxima Centauri, is a little over 4.2 light-years away. This means that even if we traveled at the maximum speed currently possible in the universe, which is the speed of light, the journey would take more than 4 years. Despite contemporary advancements in technology, achieving these speeds is still impossible. Even with the most advanced propulsion technology currently available, such as nuclear or ion propulsion, it would take a spacecraft decades, if not centuries, to reach the nearest stars. To overcome this problem, the best option is to develop new engine technologies that can achieve much greater speeds. Various concepts on how to achieve that are being considered, including the idea of using antimatter, thermonuclear fusion, or even harnessing the forces of black holes. Nuclear fusion, the process that powers the sun and other stars, involves combining two light atomic nuclei, such as hydrogen, to form a heavier nucleus and release the energy. Although nuclear fusion technology is still in its infancy on Earth, it has the potential to provide an almost limitless source of energy and could be used to power spacecraft engines. However, these feats of technology are still purely theoretical, and there is no telling whether they will ever be possible in practice or safe enough to use. The complexity of interstellar travel as a concept is exacerbated by the astronomical amount of fuel and energy required to travel such great distances. The traditional rocket propulsion technology relies on huge amounts of fuel propelling spacecraft at a speed only a fraction of the speed of light. For instance, the Parker Solar Probe is the fastest traveling spacecraft ever built by humans, and can only reach the speed of 119.4 miles per second. For reference, this is only 0.064% of the speed of light. In order for us to reach Alpha Centauri in human lifetime or less, we need to figure out how to develop a speed of at least 10% of the speed of light. However, the paradoxical nature of this task is that in order to increase the speed of the spacecraft, we need more fuel. By carrying more fuel on board the ship, the weight of the vessel increases, which subsequently reduces its speed. Sounds like a vicious circle. Nuclear or ion propulsion engines are the most advanced propulsion technology that's currently available. Offering much greater efficiency in terms of fuel consumption, they still require a significant amount of fuel to generate the required power. To overcome these obstacles, researchers are developing completely new propulsion technologies that could harness the energy sources available in space. For instance, scientists are exploring the possibility of using solar sails, which use the energy coming from the sun, similar to the way regular sails use the wind to ensure the continuous acceleration of the spacecraft. Another solution that's been put forward is to use antimatter propulsion, which would allow the spacecraft to achieve much greater speeds while consuming less fuel. Antimatter is a unique substance that has the same mass as regular matter, but with the opposite electric charge. When matter and antimatter come into contact, they annihilate each other, releasing tremendous amounts of energy. Antimatter is capable of delivering much denser energy than any technology currently available. Theoretical calculations suggest that a spacecraft functioning on antimatter could potentially reach up to 90% of the speed of light. This would mean it could reach Proxima Centauri in just over 4 years. Scientists have been conducting experiments with antimatter for decades. One of the earliest experiments involved creating antiprotons, which are the antimatter equivalent of protona. The first antiprotons were generated in 1955 by a group of scientists at the Lawrence Berkeley National Laboratory in California. However, antimatter is very costly and difficult to produce, and the technology to use it for propulsion is still at an experimental stage. Furthermore, antimatter is highly unstable and difficult to store. Its particles cannot be stored in a traditional container, as they would quickly come into contact with matter and destroy each other. Instead, magnetic fields were developed specifically for the task of capturing and storing antimatter. To sum up, the need for large amounts of fuel and energy for interstellar travel poses enormous challenges for the progress. However, developing a completely new propulsion technology or harnessing energy from sources available in space is definitely a necessary push in the right direction. Once we find a way to travel fast enough, we still won't be ready for interstellar travel, since even Columbus did not travel blindly in his search for a new route to India. Navigation and communication during interstellar travel present another major challenge for manned missions. The great distances between stars means that there could be significant delays in communication with Earth. This would make real-time communication difficult or even impossible. Furthermore, signals from Earth could be faced with interference, noise, or they could become completely lost, making data acquisition and interpretation very difficult. To resolve these issues, spacecraft will require advanced communication and navigation systems capable of handling the unique demand of interstellar travel. One possible way to do that is to use a network of interstellar satellites that could relay information between Earth and the ship, ensuring faster and more reliable communications. Another promising solution is quantum communications technology, which uses entangled quantum particles to transmit information instantaneously over long distances. This technology could revolutionize interstellar communications by allowing real-time transmission of data without any delay or interference. Another option is to use advanced artificial intelligence that could help spacecraft navigate the vast expanses between stars and adjust course as needed, even without any involvement of a human controller. Accurate navigation is key for successful interstellar travel. Even the slightest deviation can throw a spacecraft off course for millions of miles. To minimize the risk of this happening, the ships will need incredibly accurate navigation systems, such as ones using pulsars as reference points. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation from their poles. Think of them like cosmic beacons. As the pulsar rotates, it sends out the beam of radiation that shoots through space, creating a so-called momentum. Pulsars are incredibly reliable and predictable, making them ideal candidates for deep space navigation. For example, the technology of gravity assist trajectory used on the New Horizons spacecraft mission to Pluto relied on Jupiter's gravitational forces to guide the spacecraft to its target. However, as with any complex system, there is always a risk of hardware malfunctioning in some way. Without human intervention in real time, these failures can have catastrophic consequences, potentially leading to the loss of the crew and the mission as a whole. That is why, in the absence of accurate and reliable communication and navigation systems, a mission to the nearest stars would not have any success. But no matter how highly equipped the ship is, as it rushes towards distant stars, the most important component of the mission are still the people on board. The most important task in interstellar travel is to provide the crew with sufficient resources to survive during the journey. This includes developing life support systems that could provide enough food, water, and oxygen. With current technology, it is only possible to store a limited amount of resources, not enough for truly long journeys. Therefore, we need new technologies and ways to sustain life while traveling over a long distance. One potential solution is to develop regenerative life support systems that can recycle waste and convert it into useful resources. Additionally, the development of advanced food-growing and oxygen-producing systems aboard spacecraft is a must in research. Another option is to put astronauts into deep sleep for the duration of their journey, similar to the way animals hibernate in winter. Scientists are exploring the use of this technique known as suspended animation or hibernation, although at the moment it presents significant medical challenges as to how to keep the crew in this suspended state for long periods of time without causing serious health issues, which could significantly reduce the resources and life support systems required. Moreover, prolonged exposure to zero gravity can have detrimental effects on the human body. It leads to muscle atrophy, loss of bone density, and other physical changes. Therefore, to maintain the health of the crew during the journey, physical exercise and medical intervention may be required. To counteract the negative effects of zero gravity, what may help is an artificial gravity system in place. One way to do that is to maintain the constant rotation of the spacecraft. The centrifugal force created by rotation can mimic the gravitational force that we experience on Earth. This approach has been researched and successfully tested on various space missions, including Skylab and the International Space Station. Another major health concern when it comes to interstellar travel is radiation. Space is riddled with an endless array of radioactive emissions, long-term exposure to which poses a significant health risk to astronauts. Outside of Earth's protective magnetic field, humans are exposed to high levels of ionizing radiation, including cosmic rays and solar flares. Radiation causes damage to human cells, leading to various health problems, including cancer and other illnesses. Additionally, exposure to cosmic radiation can cause genetic damage to DNA that can be passed to future generations. To reduce the risk associated with radiation exposure, interstellar spacecraft must be designed in a way that shields the crew. This shield must be strong enough to block harmful radiation while at the same time being light enough to not significantly increase the weight of the spacecraft. It must be adapted to all types of radiation that the spacecraft may encounter during its journey. To address these issues, researchers are exploring various options for protection against radiation, including the use of artificial magnetic fields, as well as advanced technologies and specialty materials. In addition, the crew may need to take special medications or undergo medical procedures to reduce the effects of radiation sickness. In addition to the tiniest radiation particles, another danger you may encounter during interstellar travel are debris and asteroids. Asteroids and comets pose a threat to the spacecraft because they're difficult to detect and avoid. Space debris can cause significant damage to the ship, and even a small item moving at a high speed can cause catastrophic damage to a vessel. To ensure the safety of astronauts and the spacecraft itself, some form of protection is required. Shielding of the spacecraft from danger can be achieved through a variety of methods, including building thick walls and using material that would absorb or deflect radiation and debris. Additionally, the spacecraft could be equipped with sensors and detection systems to help identify potential hazards and avoid them. However, we're once again faced with the fact that the materials needed for effective protection are rather heavy. Although security technologies and detection systems have advanced significantly in recent years, further research and development is required to overcome these obstacles and ensure the safety of astronauts and spacecraft. Either way, interstellar travel is an ambitious goal that will require significant investment and resources from governments and private entities around the world. The cost of interstellar travel will include research and development of new propulsion systems, life support systems, navigation and communications technology, protection from radiation and interstellar hazards, and more. The cost of developing the necessary infrastructure and technologies is likely to be prohibitive and will require significant cooperation and commitment from the global community. It's also possible that conflict of interest or opposing investor agendas could cause controversy and impede progress, which could ultimately limit the scope of interstellar research and development. One possible solution to offset the cost of interstellar travel could be the development of space mining technology. Space mining involves extracting valuable resources from asteroids and other celestial bodies that could potentially provide funding for interstellar missions. Furthermore, advances in space manufacturing and 3D printing could make it possible to create spacecraft and other materials directly in outer space, reducing the cost of launching them from Earth. Without a long-term commitment to developing the necessary infrastructure, technologies, and resources, interstellar travel may remain out of reach for humankind. Conceptually, a completely different approach to interstellar travel is the construction of a generation ship. A generation ship is a hypothetical spacecraft for interstellar travel, requiring an indefinite number of generations before they reach their final destination. Instead of trying to reach a destination within the lifetime of the initial crew, these spaceships would carry generations of passengers who are born and live their entire lives on the spacecraft. The generation spacecraft concept has been proposed as a potential solution to some of the challenges of interstellar travel, including significant distances and the limitations of current propulsion technology. By allowing multiple generations of passengers to be born and raised during the journey, one can envision a scenario in which the crew can maintain the necessary resources and technology to complete the mission, even if it takes an extremely long time. However, this concept is not without its flaws. We must resolve the issues of recruiting and managing crew, allocating resources, and maintaining social cohesion over long periods of time. Moreover, there's a possibility that the knowledge and technology needed for the mission may degrade or be lost over time, which could jeopardize the success of the mission. Despite these issues, the concept of generation spacecraft remains a popular topic in science fiction and theoretical discussions about interstellar travel. To sum everything up, let's recall the classic walk-wait dilemma, which is a common predicament in decision-making. It occurs when a person must make a choice between expecting a more desirable outcome or taking immediate action to achieve a less desirable but still acceptable outcome. For instance, it may occur when you're waiting at a bus stop, but the waiting time may exceed the time required to arrive at the destination in another way, such as on foot. This scenario can be applied to interstellar travel, presenting us with a dilemma of whether we should launch interstellar ships now or wait for technologies that will generate greater speed and allow new ships to reach destinations faster. The ethical dilemma here is whether it would be fair to the crew of the first ships to make a senseless sacrifice in case the rate of technological advancement suddenly surpassed that of the first ships. Put yourself in the shoes of a pioneering crew member in another star system. You've spent decades or even centuries in space wondering if newer and faster ships may have arrived at your destination long before you. This dilemma raises deep questions about the value of human life, the responsibility for space exploration, and the importance of progress. Waiting for new technologies could lead to faster, more efficient travel, but it could also mean that the first crew would suffer or be exposed to dangers that future generations may not even have to face. Conversely, launching ships now can be seen as unfair to the crew, as they will not benefit from the same advanced technology that future generations will. Ultimately, the final decision will depend on how society perceives the importance of progress and research in relation to the value of human life. In a quest to understand the vast and mysterious universe, science has long mastered the powerful tool of logic. But even when using the most rigorous methods and the most advanced technologies, paradoxes inevitably arise, contradictions that challenge our understanding of the world. One such paradox is the dark sky at night. How is it possible that we're surrounded by an infinite number of shining stars, and yet the sky remains dark? The other is the nature of dark matter, an elusive substance that escapes the grasp of even the most advanced instruments. And what about the inevitability of oblivion? The solar system, along with our planet and ourselves, may eventually disappear into oblivion, forever lost in the vastness of time and space. These paradoxes are not just philosophical ruminations. They have real implications for our understanding of the universe. They force us to reconsider our assumptions and question the things we think we're sure of. They encourage us to go beyond our current understanding and delve deeper into the mysteries of the cosmos. And in the end, faced with these paradoxes, we can gain new understanding and move forward in our comprehension of the universe. The Horizon Problem. The horizon paradox, also known as the horizon problem, is a paradox arising from the observations that the temperature of the cosmic microwave background radiation, or CMB, is practically uniform throughout space, despite the fact that regions of the universe separated by vast distances have not had enough time to reach thermal equilibrium. The root cause of the horizon problem is that the CMB is a remnant of the time the universe was in a hot and dense state known as the Big Bang. The CMB is the almost perfect black-body radiation, characterized by the uniform temperature of approximately 2.7 Kelvin in all directions. However, if the universe continued to expand, in about 13.8 billion years, certain regions of the universe separated by such vast distances would not have time to reach thermal equilibrium and therefore be of the same temperature. This paradox suggests that the temperature of the CMB does not have to be the same throughout the universe. The horizon problem has baffled cosmologists for decades and prompted a number of proposed solutions. One solution is the theory of cosmic inflation, which states that the universe underwent a rapid expansion in the early stages of its formation. This expansion would have smoothed out any initial fluctuations in temperature, making the temperature of the CMB about the same throughout the universe. Inflation models also explain the homogeneity and isotropy of the universe, two more major observational mysteries in cosmology. Another possible answer is the concept of causality. Causality is a fundamental principle in the sciences. It's the idea that every occurrence, action, or event is preceded by a cause that determines its effect. The idea is that the early universe was in equilibrium and was much denser and hotter. Photons of relic radiation in this state of the universe were in casual contact. That meant they could interact with each other and achieve thermal equilibrium. The third solution is the concept of cosmic variance. The gist of this idea is that the universe is much larger than we can observe, and temperature fluctuations are simply statistical deviations from the average temperature of the universe. In general, the horizon paradox is a complex and multidimensional problem that has not yet been fully resolved. Each of the proposed solutions has its own strengths and weaknesses, and a true resolution of the paradox may require a combination of these ideas or even an entirely new theory. Olber's paradox. Olber's paradox, also known as the redshift paradox, is a mystery that's puzzled astronomers for centuries, named after the pioneering German astronomer Heinrich Olbers. This paradox arises from the contradiction between the presumably infinite number of stars in the universe and the darkness of the night sky. The gist of the paradox lies in the fact that if the universe were truly infinite and eternal, and the stars were evenly distributed throughout the endless bounds of outer space, then in any direction we looked, we would see a star. The light from these stars, however distant, would eventually reach our planet. Therefore, the night sky should be illuminated with the same intensity as the surface of the sun. However, despite this logical reasoning, the night sky remains dark, presenting a perplexing enigma for scientists and stargazers alike. Several possible solutions have been put forward to explain this mystery. One solution is that the universe is not uniform and isotropic, meaning that the stars are not evenly distributed throughout space. This could be due to the presence of large-scale structures such as galaxy clusters and voids that would create dark patches in the night sky. In addition, light from the more distant stars could be absorbed by intergalactic dust, making the night sky appear darker. This theory is supported by observations of major redshifts in distant quasars. Another possible solution lies in the expansion of the universe. The farther back we look, the further away the light sources would be from us. When we look back into the past, the universe becomes denser, more hotter and brighter. As a result, the light from distant stars is shifted to the red end of the spectrum and therefore become too faint to be seen. We can't say for sure whether our universe is infinite, but according to the Big Bang Theory, we know one thing for sure: our universe has a beginning. Additionally, the assumption that the universe is a finite would mean that the light from distant stars does not reach us simply because our universe is constantly expanding. Because of this, the wavelength of the light from distant stars is greatly stretched, and it eventually reaches Earth in the infrared range. It would also mean that the light from distant stars has either not yet managed to reach us, or the stars have already died out. On the other hand, if we assume that our universe is infinite, then it's quite natural that at some point, due to the constant expansion of the universe, stars and matter would begin to acquire a speed that exceeds the speed of light. This would make it impossible for light to reach Earth. The enigma of the Olbers paradox remains one of the most intriguing mysteries in cosmology, and its solution requires a deeper understanding of the nature and structure of our universe. The flatness problem. The flatness problem is a paradox that arises from the observation that the universe is almost perfectly flat, despite the fact that the density of its matter is far from sufficient to maintain such a state, which begs the question, why is the universe flat? And what do we mean when we classify it as such? The flatness of the universe means that space-time is not curved and the amount of matter and energy is just right for the universe to be flat. However, the density of matter and gravitational energy in the universe are much lower than necessary, which should cause it to either expand too quickly or collapse. And this, of course, makes us wonder, how does the universe maintain its flat shape? In a nutshell, that's the essential principle of the flatness problem, a mystery that continues to haunt some of the greatest minds in the field. There are several possible solutions to the flatness paradox. One potential solution is the elusive concept of dark energy. It is believed this mysterious form of energy contributes to the acceleration of the expansion of the universe. Dark energy is believed to contribute 68% of the total energy in the present-day observable universe. It has negative pressure and acts as a repulsive force, counteracting the gravitational force of matter and causing the universe to expand at an accelerated rate. This acceleration would help to flatten the universe. Another solution is the concept of inflation. According to the theory of inflation, the universe underwent a rapid expansion in the early stages of its formation. As space expands, the geometry of space becomes flatter. To help you understand, imagine a balloon. As it fills with air and inflates, its surface becomes smoother and flatter. This type of expansion would smooth out any initial density changes, making the universe nearly flat. The third solution is the multiverse theory, which suggests that our universe is just one of many. According to this theory, there are a large number of universes, and based on this, the likelihood that one of them will be flat is much higher than if there was only one universe. The monopole paradox. The monopole paradox is yet another example of an unyielding mystery of the universe. This is a paradox that comes from the observation that there are no observable magnetic monopoles, despite the fact that their existence is predicted by several theories of particle physics and should be present in the universe. Magnetic monopoles are hypothetical particles with a single magnetic pole, while all known magnets have a north and south pole. The existence of these hypothetical particles has been predicted in theories such as the Grand Unified Theory, a Grand Unified Theory or GUT, and quantum gravity theories. However, despite great efforts and extensive research, no magnetic monopoles have been found. Nonetheless, despite their elusive nature, there are many theories attempting to explain their apparent absence. One possible explanation for the absence of magnetic monopoles is their instability. That causes them to decay into other particles, making them undetectable in the modern universe. Another theory claims that magnetic monopoles were created during a supersymmetry transition in the early universe, but they're now too rare for us to be able to observe them. The idea is that in the early universe, the symmetry of the laws of physics was different than it is now, and these symmetries were broken during a phase transition, similar to how water changes from a liquid to a solid when it freezes. During this phase transition, magnetic monopoles should have appeared as a result of breaking symmetry. However, as the universe has expanded and cooled, these monopoles have diluted and are now too rare to be observed. The search for these hypothetical particles continues, as does the scientific work with a goal to unravel the monopole paradox and deepen our understanding of the universe. The entropy paradox. The entropy paradox is a paradox that arises from the observation that the universe is ordered and structured. despite the fact that the second law of thermodynamics states that entropy, or in other words, disorder, must increase over time. But what does entropy actually mean? We usually talk about it as if it were a measure of disorder, a quantitative representation of the randomness and chaos that exist within a system. A broken egg on the floor has more entropy than an intact egg on the countertop. A spoonful of cold cream and a cup of hot coffee have less entropy than the combination of both stirred together. A chaotic pile of clothing has a higher entropy than a neat set of drawers where all the clothes are folded and organized. According to the second law of thermodynamics, the total entropy of an isolated system will always increase over time. The law implies that the universe should become less ordered as time goes by. However, the very structure of the universe contradicts this idea. We observe that the universe is highly ordered and structured. It contains galaxies, stars, planets, and even life forms. There are several theories that offer possible solutions to this paradox. Each of these solutions offers a different perspective on how the order and structure observed in our universe can be reconciled with the second law of thermodynamics. One solution is the concept of entropy as an arrow of time. The arrow of time is the idea that time has a direction moving from the past and into the future. This concept suggests that while entropy would increase in a closed system, it doesn't necessarily happen in an open system like the universe. At the same time, it can still freely exchange matter and energy with the environment, which makes the second law of thermodynamics inapplicable. Another solution, known as the emergence theory, suggests that at the macroscopic level, structures and order can emerge spontaneously, even though entropy increases at the microscopic level. This idea suggests that while entropy increases on a small scale, it can lead to order on a larger scale. Finally, some scientists believe that the answer to the entropy paradox may be provided by the expansion of the universe. The expansion of the universe increases the volume of the observable universe, which in turn reduces the entropy of the system. This means that even though entropy increases locally, the overall entropy of the universe can remain constant or even decrease due to the universe expanding. The last two theories are similar in concept and could potentially complement each other in solving the entropy paradox. The expansion theory offers a solution to the paradox by decreasing the total entropy of the system, while the emergence theory offers a solution by explaining how structures and order can spontaneously emerge despite an increase in entropy. The information paradox. The information paradox, also called the black hole information paradox or Hawking's paradox, is a problem in theoretical physics. It suggests that black holes absorb information, thereby irretrievably destroying it. But what do we mean by information? Information in the context of this paradox refers to quantum parameters that describe the state of a physical system. These parameters contain all the information needed to fully define the state of the system. They play a central role in the principles of quantum mechanics. Quantum mechanics believes that the entirety of information in the universe is conserved, meaning that it can neither be created nor destroyed. Now, let's go back to how this paradox arises. It happens because of the contradiction between the two most established theories in physics: quantum mechanics and the general theory of relativity. Up to a certain point, the laws remain intact and have no effect on each other. But this only happens before the Hawking radiation comes into play. The information paradox was first brought to the forefront of scientific discourse by Stephen Hawking in the 1970s. He proposed that black holes emit thermal radiation that lacks any information about the matter that has entered the black hole. This led to the idea that information is forever lost when it enters a black hole, and the fundamental laws of physics are not deterministic. The information paradox has been the subject of much discussion and research in the decades following its discovery. One proposed solution is black hole complementarity, an idea that suggests that the information sucked into a black hole is not actually lost, but is instead encoded on the black hole horizon in a way that's consistent with both quantum mechanics and the general theory of relativity. To represent the complementarity of black holes, it's important to consider the same physical process from two different points of view. From the point of view of an observer outside the black hole, the information entering it seems to be lost forever, as it's pulled toward the singularity at its center. However, from the point of view of an observer from within a black hole, this information is encoded on the horizon in a way that's consistent with quantum mechanics. The key to understanding the complementarity of black holes is to recognize that a black hole's horizon is the boundary between two different regions of space-time. On one side of the horizon, the laws of general relativity operate, and on the other, the law of quantum mechanics. Information falling into a black hole is encoded on the horizon in a way that is consistent with both sets of laws, providing a possible solution to the information paradox. Another proposed solution is the firewall paradox, which states that information is not lost, but instead stored by a firewall of high-energy particles surrounding the black hole. Despite all the aforementioned theories, the information paradox remains one of the most difficult and important unsolved mysteries in theoretical physics. It is integral for our understanding of the nature of black holes, the principles of quantum mechanics and general relativity, and most importantly, the ultimate fate of the universe. Dark matter and dark energy paradox. The dark matter-dark energy paradox, also known as Bentley's paradox, is a problem in physics that arises from a discrepancy between the observed behavior of galaxies and other large-scale structures of the universe and the predictions of the standard model of the universe. A key piece of evidence for the existence of dark matter and dark energy is the observed gravitational effects of these mysterious substances. The standard model of cosmology based on general relativity predicts that the observed gravitational effects of the rotation curves of galaxies and the large-scale structures of galaxy clusters must be much weaker than they actually are. The discrepancy is known as the gravitational paradox, and it's led scientists to suggest the existence of dark matter and dark energy to compensate for those gravitational effects. Dark matter is estimated to make up about 27% of the universe, and it's speculated to exist based on its gravitational effect on visible matter. It doesn't interact with light or other forms of electromagnetic radiation, which makes it difficult to detect directly. Scientists have proposed various candidates for the role of dark matter, including WIMPs, WIMPs, weakly interacting massive particles, and axions. However, despite decades of research, neither of them have been detected with any degree of certainty. Scientists also believe that dark energy makes up about 68% of the observable universe and is responsible for the acceleration of the expansion of the universe. Its existence is confirmed based on observations, but the nature of dark energy is not entirely clear. The most popular explanation for dark energy is the cosmological constant, proposed by Einstein, which is a form of energy evenly distributed throughout the universe. However, this explanation raises some issues such as the cosmological constant problem and the coincidence problem. These problems stem from the fact that the observed value of cosmological constant is much lower than the theoretical predictions, as well as the fact that it has the same order of magnitude as the density of dark matter. It's also worth mentioning that the current standard model of cosmology, the Lambda CDM model, which uses the concept of dark matter and dark energy, corresponds with a wide range of observational data and is considered the most successful model of the universe to date. Bentley's paradox refers to the fact that even though dark matter and dark energy make up such a significant part of the universe, their exact nature remains a mystery. Many theories have been put forward to explain their properties, but none have been conclusively proven to be accurate. The discovery of new particles or new phenomena that could help explain the nature of dark matter and dark energy would be a major breakthrough in our understanding of the universe. The paradoxes that arise when exploring the universe and its governing laws are not obstacles, but rather opportunities for growth and development. They represent a puzzle that pushes the boundaries of our understanding and requires new theories and explanations, lighting a spark for further research in the field of cosmology. Each resolution of a paradox is a step towards not only in solving a particular problem, but also towards our overall understanding of the intricacies of our universe. At some point of our lives, we have probably all wondered if we are alone in the universe. It would seem that in our own or in other distant galaxies, there are so many planets that revolve around numerous stars. So why have we still not encountered any traces of extraterrestrial life? But what if advanced alien life forms have been around for a long time, and they're simply hiding? According to the dark forest hypothesis, technologically advanced civilizations outside of the solar system may already be thriving. However, they have no intention of making contact because they are either cautious of potential attacks from other civilizations, or they may be indeed preparing to attack. Today, you'll learn about the dark forest theory and why you should probably be afraid of being heard by someone in the vast cosmos. 1. The Dark Forest Hypothesis, the author and original source. The author of the Dark Forest Hypothesis, DFH, is science fiction writer Liu Cixin. It's worth noting that this is not a scientific theory, and it's not based on any concrete evidence. In 2008, Liu Cixin published his successful fiction novel titled The Dark Forest. The dark forest theory was first outlined in this book. The gist of the theory is that every civilization on a cosmic scale seeks to obtain the resources necessary for its continued survival. Therefore, any extraterrestrial life hides in order to not be destroyed by another civilization, and also in order to be able to attack and ensure its own survival. So why is this theory called the Dark Forest Hypothesis? In his novel, Liu Cixin compares this to precarious coexistence to a forest inhabited only by hunters. The author paints civilizations as metaphorical armed shooters in a dark forest, who silently move forward, afraid of being discovered by fellow hunters. If one hunter managed to find another, it's in their best interest to attack first before the enemy does the same. Based on this, we can name several ideas that are promoted by DFH. First one is that hypothetically, alien civilizations exist, but they are in hiding due to the risk of being attacked by others and losing acquired resources, such as inhabited planets. Within the construct of the Dark Forest Hypothesis, survival as the basis of every civilization is known as the chain of suspicion. This phenomenon is caused by insufficient communication, which leads to mistrust as a direct result. The second idea is that a civilization that gives away its location by actively transmitting, say, radio signals, could be captured or destroyed by others for resources. The third concept is that fellowship in this type of system is exceedingly rare, since every civilization strives above all to survive through expansion. However, a treaty is possible if the terms are beneficial to both civilizations. Lu Cixin represents the universe as a battlefield for limited resources, where an alliance is practically impossible. Finally, it's important to note that in Lu Cixin's hypothesis, these hunters are analogous to civilizations with a high level of technological advancement. Therefore, if any civilization is not sufficiently developed to announce itself in space, it will either go unnoticed or it may become easy prey. 2. DFH is an answer to the Fermi paradox. As you may already know, in 1950, famous physicist Enrico Fermi, when discussing the phenomenon of flying saucers with his colleagues, unexpectedly asked, "Where is everyone?" referring to examples of extraterrestrial life, which marked the beginning of the famous Fermi paradox. We discussed it in detail in this video on our channel. Fermi assumed that if our galaxy formed several million years before the birth of mankind, then it is possible that other civilizations could have emerged during this period, much older than Earthlings. Therefore, the Milky Way galaxy should be full of civilizations, which could pick up our signals due to their much more advanced technological development, as well as travel through the galaxy. However, so far we have not seen any traces of alien activity. Why haven't they visited Earth yet or come close to our planet? To determine the potential number of extraterrestrial civilizations that exist within our galaxy, the famous Drake equation was derived in 1961. However, we cannot use it to learn why alien creatures have not left any signs of their life. Therefore, at the moment, the Fermi paradox only has theoretical explanations. Additionally, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very small. 1 in 10 billion trillion, which is to say 1 times 10 to the 22nd. The professor suggests that our evolution was not unique and other civilizations could potentially have existed before us or even much longer before us. There are more than 70 hypothetical solutions to this issue, one of which is the dark forest hypothesis. Of course, we cannot check the veracity of DFH due to our current technological limitations. However, Lu Cixin's theory provides a logical explanation as to why we still haven't picked up a single alien signal or found any clear signs of life on other planets. It's simply dangerous for other civilizations to betray their location for fear of invasion. Although this hypothesis presents very clearly defined ideas, DFH still has some inaccuracies. For example, if other civilizations exist, then they must differ from ours when it comes to the level of development due to different periods of origin, as Fermi pointed out. This means that there may be civilizations of our technological level or higher that actively search for alien life or study their own systems just like us, because they don't see it as a threat. Therefore, we may not be the only ones sending signals out there, because civilizations do not necessarily develop in fear of detection if they have not experienced confrontation. 3. More about the assumptions of dark forest hypothesis. The idea of capturing other territories and the possible destruction of the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and wars. There are a lot of reasons why people conquer and establish power over other nations. However, in most cases, such as during the colonization of Africa by the Europeans in the 19th century, the main motivation were land and natural resources. The rapid industrial development in Europe required more resources, which were abundant on another continent. Therefore, the colonization of Africa contributed to the development of European countries, but the African land and its population suffered from this expansion. The DFH offers the same colonial model as the reason why one civilization would attack another. We're still pursuing the goal of expansion for the continued survival of mankind, studying exoplanets and other star systems, and planning the colonization of Mars. The red planet is also rich in natural resources that are needed for technological development. Therefore, if we assume that another civilization pursues the same goals, we may have to fight for lands that could serve humanity. Otherwise, our survival would be under threat because, according to this hypothesis, survival and the necessary resources are crucial for the preservation of the species. In addition to the need to replenish a limited resource, there are other reasons for the aggressive behavior by civilizations. For example, as we've already said, the DFH introduces a concept known as the chain of suspicion. This concept is closely related to another aspect of this hypothesis, which is known as the technological explosion. The gist of the chain of suspicion is that it's impossible for civilizations to know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to the researcher Chao Yu, this chain can only emerge between civilizations with the same level of technological development, since they can likely objectively assess their own and other people's capabilities. Thus, if there is a significant gap in their respective levels of development, the chain cannot be formed. The technological explosion describes the ability of cosmic civilizations to make rapid scientific and technological leaps. A strong new hunter can pose a threat to others, because advanced civilizations can start to be wary of it or seek to destroy it. However, Chao Yu points out that any invasion attempt could also harm the attacker, as other civilizations with similar or higher levels of advancement would be able to detect it, which would contribute to the chain of suspicion. However, in spite of the clear advantage in attacking other civilizations and in stealth, the DFH considers another scenario: benevolence. The point of benevolence is to refuse to attack other civilizations, even if they are detected, and they will probably be able to respond to the signal. In a dark forest, this tactic is very dangerous because it is again reinforced by the chain of suspicion. Found by a benevolent civilization, another civilization may turn out to be aggressive or rapidly developing. Therefore, in the future, it will be able to destroy others and survive, having collected enough resources, whereas the benevolent civilization will most likely cease to exist. If we assume that extraterrestrial life really exists, and it is way more advanced than us, then it might attack us, since this is a survival tactic with the highest chance of success. This is not the best news. So then, are there other ways for the events to unfold that are beneficial for Earth based on the dark forest hypothesis besides an attack on our planet? Let's look at this in terms of game theory. Number 4, game theory and DFH. The point of game theory is to learn how people make decisions based on certain conditions in order to achieve the best result. So let's imagine Earth as civilization A and a more advanced alien life as civilization B. Let's assume that B has picked up on our radio signal. Now B has 3 strategies for action: attack, remain unnoticed but become suspicious, or respond with a prospect of possible friendship. Attack will be considered the most advantageous strategy, even if A is able to fight back. On the other hand, this scenario might turn out to be a losing one for B if A, according to researcher Alina Su, can send a signal in order to transmit the coordinates of the planet of civilization B to other civilizations. Perhaps in this case, the best option would be to remain unnoticed. If both civilizations don't do anything, neither will benefit. On the one hand, this will save A and B from danger, but on the other hand, they won't be able to obtain the necessary resources. There's also an option to make friends. If both civilizations agree to an alliance, then one of them will benefit, for example, from the ability to use alien technology. The other civilization, the one that proposed friendship, would also be able to benefit, albeit slightly less. Does that mean that an alliance is the best scenario for both civilizations? Possibly, but it comes with some caveats. Firstly, benevolence, as you already know, is very dangerous because, hypothetically, extraterrestrial civilizations are unlikely to be friendly too often. Secondly, the potential amount of resources that would be obtained, even if a trade deal is established, is less than what you would gain with a forced takeover. And so, the theoretical attack on Earth has the highest probability, but this course of events can greatly harm the attacker. Still, other civilizations may be afraid of the unknown military potential of Earth, and therefore choose the tactics of secrecy or friendship. 5. The danger of sending signals into space. Does it mean that if the probability of Earth being conquered is higher than any other option, should we be wary of the propagation of our signal into space? According to DFH, messages to other civilizations could threaten our security. The same opinion is shared by many astrophysicists, including Stephen Hawking. After a breakthrough in space research in the middle of the last century, there was plenty of interest from scientists in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since that time, several radio messages have been launched into space, the latest of which dates back to 2017. Physicist Stephen Hawking believed that these messages could lead to the scenario described in The Dark Forest. According to him, an alien civilization visiting Earth could have the same consequences for us as the effects colonization of America had on its native inhabitants in the 15th century. Therefore, he expressed an opinion that this type of communication must be stopped. Nonetheless, other scientists, including SETI astrobiologist Douglas Vakoch, believe that the fear of sending messages can lead to Earth's isolationism. Moreover, Vakoch pointed out that the alien civilizations have had a chance to attack our planet while it was just developing, so you should not be afraid of the possibility of being heard by extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunters' behavior. That is, not all alien civilizations would definitely attack us if they detected our signal. Additionally, a group of independent researchers led by the Global Catastrophic Risk Institute, Seth Baum, suggested that in addition to potentially dangerous civilizations, those with a lesser potential to harm us may also exist. They believe that there might be neutral civilizations that prefer to hide and not make contact, as well as civilizations that could establish a friendly relationship with Earth and help us solve global problems. In conclusion, the dark forest hypothesis is not the sole answer to the burning question, where is everyone? There are many other suggestions that attempt to explain the lack of a hint of extraterrestrial life, such as too great of a distance between civilizations, or the low likelihood of the emergence of other living organisms. Nevertheless, we cannot rule out the possibility of the veracity of Liu Cixin's theory, but we cannot confirm it either. All of us probably watched science fiction films and wondered what aliens may look like. Many people imagine extraterrestrial life similar to us, carbon-based, but with a few biological differences. And others imagine it as something completely unlike humans. And so the famous author of The Laws of Robotics, science fiction writer Isaac Asimov, describes some forms of alien life as living stones that had a silicon-based chemical composition as opposed to carbon like us. But what if we told you that silicon-based life may not be entirely fictional? Today we will delve into our biology and try to answer whether the existence of silicon-based life is possible. Carbon is the basis of our life. Without it, it is possible that we would never have come to exist. It makes up about 18%, or 26 pounds of our total body weight, and performs a structural function, forming something akin to a carcass for the molecules and organic substances necessary for our life. Proteins, fats, carbohydrates, sugars, etc., even DNA. Moreover, as you may know, carbon plays an important role for many life forms around us, such as plants. With each breath out, we exhale carbon dioxide. This gas is required for plants for photosynthesis and the production of oxygen as well as organic substances like glucose. CO2 is also the gas that traps heat in our atmosphere, which sustains all life on Earth. If it weren't for the harmful greenhouse effect, we would simply freeze. Aside from the value of carbon and its compounds in biology, it's important to mention the role it plays in manufacturing. Most of the things you see on a daily basis contain carbon. From clothes, medicine, your favorite cup of coffee, and the house you live in, to musical instruments played by your favorite musicians, and the phone or laptop on which you're watching this video. All of it couldn't exist. Of course, carbon is not the only component present in living organisms and all of the aforementioned items, but its chemical versatility and the ability to build huge chains with other elements makes carbon practically indispensable. According to astrobiologist Robert Hazen, a vital chemical element must be able to actively form bonds with other elements and not be too reactive at the same time, so as not to combust during these interactions. Furthermore, this element must form strong, long-term bonds and be able to store and transmit information. Carbon meets these criteria, therefore is superior among the most important building blocks on Earth and beyond. However, is carbon really the only possible foundation for life? What if it was simply erased from outer space? What element could then replace carbon? The possible answer can be found right under carbon in the periodic table: silicon. Silicon is one of the most common elements on Earth. Its core contains about 28% of its total mass. This element can be found in sand, amethyst, clay, granite, etc. Like carbon, silicon has a wide range of applications and is a valuable element in our life. Many processors in phones and computers use silicon as an accessible alternative. Silicon is also used to form conformable silicone compounds, which have applications in cosmetic and medical industries, ranging from hair conditioners to contact lenses, as well as aviation and construction spheres, like in sealants and nonstick paint. So what role does silicon play in our biological life? According to researcher Milton Wainwright, it's likely that silicon may have had an effect on the emergence of life on Earth. According to his research, silicon that comes from outer space may stimulate bacteria growth, even if there's a lack of nutrients. The scientists therefore suggest that billions of years ago, during the birth of the solar system, comets containing silicon may have bombarded Earth, which caused the development of bacteria. In addition to its possible merits in the past, silicon is also a very important component in plant development and growth. Silicon protects plants from external threats, both physical and chemical, making them more resistant. It also protects the plants from disease and prevents them from losing water. Moreover, silicon is important for healthy bone development and wound healing in humans and other animals. this element may also reduce the risk of Alzheimer's and cardiovascular disease. You could say that silicon, in fact, has an auxiliary effect on our lives. So why is it being considered as a likely alternative for carbon in alien life? First, it is due to their chemical similarity. There is a reason why silicon is located right under carbon in the periodic table. Each chemical element in the table can form a chemical bond, during which the electrons of each atom are combined. Silicon and carbon are both tetravalent, meaning they can bond to 4 atoms. As such, silicon can probably form long and strong bonds with different elements, similar to carbon. Secondly, in 2016, a team of scientists from the California Institute of Technology, led by Francis Arnold, were able to synthesize molecules that are made entirely of silicon and carbon. Furthermore, according to their study, E. coli could produce the protein that contained this compound. Scientists came to the conclusion that silicon-based life is possible outside of Earth. So, in order to answer the question of whether silicon could replace carbon, we must first consider what life is in biological terms and what are the criteria for it to occur. Scientist Norman Pace believes that life is the ability of an organism to replicate itself and to develop enough to overcome evolutionary hurdles. For example, developing the ability to grow organs required for movement in order to make travel across land easier. Therefore, the building blocks of this organism must be able to quickly adapt to new conditions. In addition to chemical complexity, a number of ecological criteria must be met for life as we now know it to emerge. In short, life requires oxygen, nitrogen, moderate temperatures, and water. Many compounds are highly soluble in water, such as salt. Therefore, previously separate parts of one compound can create new bonds with other elements. Carbon can form a long and stable framework for the living cells of water-based organisms. But can silicon also make connections necessary for life to exist? The short answer is no. So, what? That's it? Silicon-based life cannot possibly exist? Not quite. Because in addition to water, there are other solvents in which life can hypothetically originate. For example, scientists speculate that liquid ammonia, which is common on Jupiter and Pluto, could serve as an alternative to water. However, NH3 is highly toxic, which may prevent silicon-based life from developing, but scientists have yet to test this theory. In addition to liquid ammonia, another potential solvent is sulfuric acid. You may note that H2SO4 is generally capable of dissolving most metals without residue, and you'd be correct, but oddly enough, it's also possible for silicon to develop in it. Therefore, hypothetically, silicon-containing organisms can develop on planets with a sulfuric acid environment, such as Venus. Silicon can also exist in other cold solvents like methane and ethane, which become liquid at low temperatures, as they do on Titan, one of Saturn's moons. However, low temperatures greatly slow down any chemical processes and solubility. Although silicon would be able to quickly combine with other elements at low temperatures, silicon compounds would not be able to dissolve very quickly. Therefore, it would be very difficult for life to emerge in such conditions. But what about the structural function of silicon? Just like carbon, silicon can combine with elements essential for our existence, including nitrogen, hydrogen, oxygen, phosphorus, sulfur, and even many metals. However, silicon is not as versatile and adaptable as carbon. In addition to the fact that silicon cannot develop in water, it will also not bond with anything at moderate temperatures between 32 and 212 degrees Fahrenheit. That means that silicon can only combine with other elements at excessively high or significantly low temperatures. which would make it very difficult for other elements to build bonds with silicon. Moreover, unlike carbon, silicon does not bond well with itself, and that is the bonds between two silicon atoms that would not be able to build a very large framework for cells. Think of a diamond. It's made entirely of carbon, which shows the strength of the compounds the element is able to form. However, the one element that silicon likes to combine with is oxygen. And this further supports the theory that silicon-based life is unlikely. On Earth, silicon is almost always found in the form of SiO2, which is basically sand, making it very difficult to separate the two elements. This means that silicon is less versatile than carbon, which forms equally strong bonds with other elements. Turns out that if we could swap carbon in our body for silicon, then instead of carbon dioxide, we would exhale sand. Aside from respiration, carbon also plays a very important role in our nutrition. Food is an excellent source of energy, which is why when we feel tired, there's nothing better than a good meal. However, our source of energy is not the food itself, but the compounds it contains, like glucose. As you may have already guessed, glucose is also made of carbon. What's more, when we don't have an opportunity to eat and we need energy, another carbon compound like starch can help us. It's deposited into the liver and used to replenish our supply of glucose when needed. However, these bonds would be unstable with silicon, which means they would not be able to properly support our life. While silicon is unlikely to replace carbon, it is possible for silicon-based life to evolve. However, it's highly doubtful that an organism that only contains silicon and no carbon in its chemical composition would be able to build complex chemical bonds. Silicon-based organisms have not yet been found on Earth, but as we've already mentioned, silicon is an important secondary component for many plants and animals. In some ways, it could probably be considered a part of ourselves. Furthermore, our ocean contains diatoms, a type of mysterious algae with cell walls made of transparent SiO2. This doesn't make this algae a silicon-based life form, but it does prove that silicon can indeed act as a building block of a living organism. As for other planets, according to a study by a team of scientists led by Ricardo Gobato, the ideal environment for the development of silicon-based life are the virtual absence of oxygen and water, temperatures above 428 degrees Fahrenheit or below 32 degrees Fahrenheit, atmospheric pressure much higher than on Earth, and a solvent like sulfuric acid or methane. Some of the planets in the solar system fit some or almost all of the criteria. For instance, Titan, the largest moon of Saturn, and possibly Venus. Titan has a multitude of methane and ethane lakes, as well as a nitrogen atmosphere, which are both excellent conditions for the origin of silicon-based life. The surface of Venus is very hot and subject to high pressure. However, the thing that makes Venus one of the candidates for silicon-based life are yellow clouds of sulfuric acid present on the planet. Hypothetically, silicon organisms could form in these clouds, although most likely, even on Venus, a molecule like that would contain significantly more carbon than silicon due to the high content of carbon in the atmosphere. Surprisingly, another candidate for the formation of silicon-based life are hypothetical carbon planets. At the moment, scientists only know of one such exoplanet, 55 Cancri e, which is located 40 light-years away from Earth. These planets likely form further from their parent star, which means they may have solvents suitable for silicon on their surface, and hypothetically, no water either. Moreover, it is possible that carbon planets are full of heavy hydrocarbons like butane, which may be suitable for silicon-carbon bonding. However, silicon-carbon compounds, silicon carbide, are very strong, which means their decomposition can take a lot of time and energy. So even if life begins to develop on a carbon planet, it will be a very long process. If we assume that silicon-based life has in fact existed for some time, then how would we recognize it? Sci-fi writers imagine a life form similar to living stones, like the authors of the Star Trek, for example.
We are dealing with a silicon creature of the deep rocks.
However, in reality, silicon-based life does not necessarily look like this, since we are also not covered in diamonds and diatoms look nothing like stone. The fact of the matter is, scientists have no idea what a silicon-based life might look like. However, they assume that silicon-based life is unlikely to resemble us in chemical complexity or even intelligence, so we probably won't get to meet stone people. Such alien organisms would also be difficult to find if not technologically advanced, because we simply would not know what molecules to look for. It is difficult for humans to imagine the possibility of life developing in conditions that are significantly different from those on Earth. The only life we've encountered so far is ourselves and the creatures surrounding us, which is why most missions sent into space focus on finding structures similar to our own. Right now, it's impossible for us to know if there is life made predominantly of silicon due to our scientific limitations. However, the cosmos is vast and diverse, so we cannot say for certain whether all alien life in billions of galaxies is carbon-based.